Okay, so thank you very much, and then thank you for having me here. I mean, it's always nice to experience this nice feeling of being like at home in the nice premises of my alma mater. So I like to come back now and then. So today I am just going to report on a joint work with Gernot and Mario Kiburg from Melbourne. And the work is about, well, we try to approach the problem of sort of universality for random matrix dynamics. Well, it is just based on ongoing work and collaboration. We managed only to publish at the moment only one archive paper, and it was mentioned on the previous transparency. So what is the outline of the talk? Well, quite a lot is known about universality of statistical problems in random matrices. You have just certain ensemble, and you know that local properties of, for example, eigenvalue spectra or correlations of eigenvalues are very universal. Less is known about dynamics, and properties like universal properties of dynamics. But of course, well, there were many contributions already. Dyson, in his one of his papers many years ago, just introduced something which is called now Dysonian random walk, and he just discussed that. Later, in the context of mesoscopic systems, open systems, or quantum transport, people discuss transmission eigenvalues in quantum wires and so on. And well, there's this the MPK famous equation, which is a sort of stochastic equation for eigenvalues and so on. So, but what we wanted to do is to look closer into microscopic properties or local properties of distributions. So, what I will do first, I will just recall two very standard stochastic processes in the matrix space, and where you will see sort of dynamics, time dynamics. And the first one, which is just the additive one, which is just related directly to idea by Dyson, and it will be just this Dysonian random walk. And the other one is multiplicative stochastic process, and I will just consider the simplest version. But in this context, you think of random matrix as a sort of transfer matrix, and it just tries to shift your system from one layer to the next time layer and so on. And if you do look at evolution operator, it is just a product of such transfer matrices. And I will consider the simplest case, and I will just imagine that this transfer matrix is just random matrix and has no structure, so it is basically given by Gini matrix. And I will tell you a couple of words what you get when you consider products of Gini matrices. And if you just well, consider time, a discrete time, well, as a sort of well, time just bringing you from layer to layer, then you start to think about sort of geometry of the system. You have certain n degrees of freedom, and you have certain number of layers, and then the discrete time corresponds to the depth of the system, and you can just talk about well, shallow and deep systems, and you have this aspect ratio, and you have just geometry of the system. And I will tell you what happens when you take large and limit. So you have many degrees of freedom, many time steps, and you keep the aspect ratio fixed. And I will just try to tell you that there's a big difference between shallow systems and deep systems. And there's a sort of phase transition in between, when the number of degrees of freedom per layer is proportional to the number of layers. And we call it a critical phase, and then I will tell you what happens in that case. And you will see what is the crucial concept in that game is something which we call width to spacing ratio. If you look closer into spectra, you imagine that you have a microscope, you look at eigenvalues, you will see that eigenvalues can form in this local scale something like a continuous spectrum or discrete spectrum, or something in between. And this is measured by a concept which we call width to spacing ratio. And I will just we try to show some results, and I will tell you that kernel, first of all, you will see that it is, well, the evolution is given by determinantal point process. So if it is given by determinantal point process, everything is defined in the kernel. which gives you a 2-point correlation. So once you find kernel, then you know everything about correlations of your eigenvalues in micro scale. So we want to find a kernel, and you will see that the kernel not only depends on symmetric class, as in the static problem, but also in addition to that, it depends on this width to spacing ratio. And finally, so having done that, I will just formulate a conjecture. I will just try to tell you that maybe when you talk about dynamics, it is not only symmetric class which matters, but also this local thing, which is width to spacing ratio. Okay, let me define the main actor in the play here. It is just a complex Gini matrix. It is made of independent, identically distributed complex entries. Well, they have zero mean and the variance, which is fixed and equal to 1. And then often I will just, when you want to take just sort of large n limit or density limit, or then you just use also rescaled version. So you just divide in each entry by square root of n. N is the dimensionality of your matrix. Then you will see that this small g, which is directly related to g, has a well-defined limiting clause. So whenever I use small letters, it will be just something which comes from rescaled Gini matrices. So let's come back to the Dysonian random walk idea. So you imagine that you have a random matrix at some moment of time, at m-1, and you add to it just a Gaussian matrix, it's a Gini matrix, you have some coefficient here. So which means that each individual entry just undergoes a random walk of the matrix. So because I mean you add it, so you just add just a little contribution, and it is a Gaussian increment. And you keep on repeating this process. And then if you do that, you just realize that what you get after n steps is just initial matrix plus the sum of Gini matrices, which is again a Gini matrix, although it has just rescaled variance and so on. And then if you look now at a Hermitized version of this matrix, then of course it is Hermitian, so it has eigenvalues which are on the real axis. And you can just look what is the evolution of that. So you have initial eigenvalues which are sitting in x naught. You place them somewhere, and then now they start to evolve. And then already Dyson realized that, well, there's a sort of repulsion between them, and coming from the logarithmic repulsion, and they never cross. It is called vicious random walk, and you have a crowd of random walks which do not intersect. And there was a lot of work like 20 years ago or 10 years ago about this subject. And then you can, of course, then later on take the continuum limit if you scale appropriately this little coefficient with time, and you can make your time continuous. So I will come later to this picture, but keep it in mind. It is the simplest realization additive random walk. And what is now the multiplicative random walk? Well, it is just constructed in the very same way. You construct it, but you don't add, but you multiply. And well, as I said, you imagine that it's a transfer matrix. The simplest assumption is it has no structure at all. It is just random. And you keep on repeating that, and you will just get a product of matrices. And you start with identity at the beginning to make things simpler. And you will see that, of course, it is a sort of evolution operator which just brings the initial state to some state after n steps. And then if you are interested how the norm of this operator changes in time, you just consider this Y matrix, which is just made out of this matrix times complex conjugate of that. It is sometimes called strain matrix. So it tells you a lot about the norm of that. And then we will be interested in that. And of course, well, since it is a multiplicative process, you want to make it simpler, you want to make it additive, so you take log of that, and you define Lyapunov matrix. And if you want to just take also large n limit, it's good to just make a density of that, and you just divide it out that thing, and then you divide something which is a Lyapunov exponent. And Lyapunov exponent itself, when you take large n limit, just becomes a variable which is a sort of deterministic. It goes to a certain value. But of course, for finite m and n, it is just a sort of random variable, and it has a certain distribution. So we are today interested in what happens to Lyapunov exponents of eigenvalues of this Y matrix when you take m and n infinity limit. And well, you can take this limit in various ways. Well, before I do that, I mean, well, you can also imagine, well, coming back to that picture, that you have some initial state, then you propagate to the next layer, and here those links tell you how you multiply by elements of G matrix, you get a next layer, and so on, and you get a system which has a certain geometry. As I said, you have n states. In this case, it is n equals 5, and you have number of layers. In this case, it is 7, and you have very simple system, which is a linear system, of course, much more complicated than the one used in neural networks. And then you may ask what happens if m, number of layers, is much larger than n when you take the limit, or when it is smaller, when it is a shallow system, or when it is proportional. So, well, just to have a control of what happens in that limit, I introduce an aspect ratio, and which is, well, I set n to infinity and make m be dependent of n, and it is an increasing function, but it may increase in various ways. And for example, if it increases as n squared, then this aspect ratio goes to 0, and then the system becomes very deep. As I said, m proportional to n is a critical system, and you can have a shallow system when n is smaller than n, like square root of n. Okay, so quite a lot is known about that, and just before I will go on, I will just tell you what we are going to do. I mean, if you have only one layer, so you have just Wishart matrix, you know quite a lot, and you can just define macroscopic and microscopic problem. Macroscopic problem is just that you send n to infinity, you introduce the small letter, and then you get the eigenvalue density, and it is Marchenko-Pastur density in that case. But we are interested not in that limit, but we want to just look closer at what happens on the scale, which are just on the distance of spacing between eigenvalues. If you have just, for example, in that case, n eigenvalues between 0 and 4, which means that the average spacing is 4 over n. So you go to 1 over n scale here, and you with your microscope, you study what is the statistics in this small scale. And then you will quickly realize that there are three possible situations. One, when you look at the edge close to the origin, it is called hard edge. It is when you have many here eigenvalues. And this soft edge, when you are close to here, the two edges are different. Because, for example, by construction, you cannot go here to negative eigenvalues of this matrix because you have always squares. While here, just you see that they a lot fluctuate for finite and around this edge, and this is why it is called edge. Or if you are in the back. So I will be first interested in the back. But to be able to compare two or more positions, it is good to unfold the spectrum. So here, if you see in macroscopic scale, the value of the density is smaller than here, so which means that spacing here is larger than here. If you want to make it independent, in a sense, if you want to compare two things, you should just somehow unify that, and the way of doing it is instead of using this lambda, you use just quanti as an observable, and quanti is uniformly distributed, so you map it from original variable to this one, and it's called unfolding, and in the unfolded scale, the spectrum is just uniform. And uniform means that, of course, eigenvalues are equispaced. So I will do that. And whenever you see the letter U, it means unfolding or uniform. And you will see, well, usually to do that you have to know the density, but you will see that in the double scaling limit m and going to infinity, you get this unfolding for free. Okay, before I just tell you what is just this microscopic limit, I will tell you what is the macroscopic limit. In the previous transparency, you saw this for m equal 1, and I call it either Wishart or Marchenko-Pastur distribution. But it turns out that you can write down a closed form formula for any m. And when you set n to infinity, but you keep the number of matrices in the product fixed. And it is given in the paper of Thorsten Neuschel, and I think you can find some traces of them before in the paper by Philip Young. But very explicit formula, and the formula comes from the Thorsten paper. And the density is given in a parametric way. You have density as a function of this argument x, and both are parameterized by a parameter phi. This parameter phi is just defined on this interval, and if you just work a little bit, then you will see that for m equal 1, you will just reconstruct this formula for Wishart matrices, or just you get Marchenko-Pastur. If you go to m equal 2, you get a more complicated formula, then you will see that two things happen. I mean, the soft edge will move to some other position, and this position is now denoted by x star, and it depends on the number of matrices in the product. When m was 1, it is 1 plus 1 to power 2, so it is 4. It was just Marchenko-Pastur, which you see here. For 2, it will be 3 to power 3 divided by 2 to power 2. It will be something like around 7. But whatever it is, I mean, it moves with m. What you see that always singularity at the soft edge is a square root. The singularity at the hard edge depends on m, but it always is integrable. It approaches to 1, but it's always integrable. Okay, once you know it, you can just work out, you can now take a double limit. You can set not only m to infinity, but also n to infinity. And if you do that, so well, if you want to take a double limit, then you also have to just define something like a quantity which has a well-defined limiting distribution. Of course, here, this y does not have a well-defined limiting distribution because the support goes to infinity. It stretches over the whole axis. But of course, what is the good thing to do? That's just to define something like a square root of m. Square root of m, it is just something like just taking density of what is just the change per layer. And this guy has a well-defined distribution, and it turns out that if you look what is the distribution coming from the other one, when you take a double scaling limit, it is uniform of 0, 1. So this guy has a uniform distribution, so it unfolds the spectrum. So it is very good because then you can really easily unfold the spectrum. So what you do, you just, instead of just matrix 1, you take the 1 over m root of that, and or if you go in the opposite direction, you just relate y to this uniformly distributed matrix, and you blow up the spectrum. Blow out the spectrum, you go to the scale, and then you look in this local scale under microscope. So you should look, instead of original eigenvalues of matrix y, into just some place which is around this quantile p, and you blow up here, and then you just express results in this variable. So it is unfolding procedure. It is relatively easy. So you can do that. So we have done that. So, but before we can, so I should tell you that, well, we started from some formulas which were known. The business about products of Shinib matrices started something like roughly just 7 years ago. We just first realized that if you have product of Shinib matrices, it is given by determinantal point process, and we found the weight. Then Gernot, Mario, and Wei just generalized it also to singular values, which means exactly to the object we need today. So we have a product times the product dagger. Then we just looked a little bit into just local properties. We looked at the Lyapunov spectrum, and the people, Liu, Wang, and Zhang look at the scale, fixed m, and going to infinity at the soft edge and the bulk. So we were very much motivated when considering soft edge by the work here. So, when I said that we found that it is determinantal point process, we also found the weight, and the weight is given in terms of something which is called Mayer-G function. It is a special sort of function, and this is function which I did not display here, but it is related to sort of integrals, and you can see here the integral which is directly related to major G functions. So it is the terminal point process, and the kernel is known explicitly. The kernel depends on two eigenvalues, and here is the form of the kernel, and we like to write it in that way because J can be now treated as just something which goes over eigensectors. And now you see the form of this function, which I said is related directly to major G function, has dependence on m, n, and the integral is over t. So now you can take various limits of that. And then, of course, what you can do, then you can just, as I said, you can unfold the arguments, and you can just take results, and you get the results in the bar and the soft edge and so on. And this is what we did. So before I just display results for you, I will just introduce the concept which I mentioned at the beginning, which is this width to spacing ratio. So you imagine that you look at your spectrum under microscope. What you can see? You can see maybe, if you are lucky, that, well, if it is a typical spacing between the two, you can see either individual links, or they can just form something like a continuous spectrum. So the good concept is just to take the width and divide by the spacing between them. So for example, spacing between this guy and this guy is just around 3, and here it is around 1/2, so this width to spacing ratio will be around 1/6 or something like that. And the width to spacing ratio, if it is much smaller than 1, locally peaks are very narrow. Then you see discrete spectrum. If they are getting broader and broader, then you see that the spectrum becomes more and more continuous. Okay? So roughly, width to spacing ratio, you take a, distribution of J's eigenvalue, you look what is the, standard deviation of the distribution, and you divide by the spacing between neighbors of this peak. And we found it in our model, and it is related to digamma functions, and we found that this, in our model, it is just given by an extremely simple formula. It is a square root of J. J is the number of eigenvalue by n. M is just number of matrices in the game. And of course you have n eigenvalues.
How do you define the width? How it's defined?
Well,
because the still spectrum is formally for any finite before you consider limits.
Yeah, what we did, we just found exactly what is just the distribution of Lyapunov exponents.
Okay.
And in the limit, when m is large, much larger than n, or actually m is much larger than j, it becomes Gaussian.
Ah, okay, and this is width of this Gaussian.
It is width of the Gaussian, and we know what are the consecutive positions.
Okay.
And the positions are just given by the gamma function, the digamma function, and the width is also related to that. And of course, well, since it's a local quantity, it doesn't matter whether you talk about the eigenvalues of y or just Lyapunov exponents and so on. So you found that. And then, of course, you see what is interesting, what is the width to spacing ratio for the rightmost, for the largest eigenvalue. And of course, it then depends on n to m, and it is on the aspect ratio of the problem. And then you can classify, well, when this aspect ratio has a certain value, this value can be 0, finite, or infinite, then you see different situations. When this aspect ratio is 0, which means m is much larger than n when you take the limit, then you see only discrete spectrum, because the leftmost width to spacing ratio is 0. Then you have this intermediate situation. It is finite here, and it changes here like square root. It becomes here more and more discrete, and finally it gets completely discrete in the closest neighborhood of that hard edge. And then finally, when the system is shallow, m is much smaller than n, then you see here it is infinity, and for any j of order n, it is just continuous. Only in a very little just region close to the hard edge, you can see something like non-trivial scaling, like this structure, and finally you have discrete spectrum here. So we have the three situations: deep system, critical system, and shallow system. And of course, when you take just double limit, you don't talk anymore about the eigenvalue number j, but you say that j is in a position which is proportional to p is a quantile of the spectrum. And when you see, it gives you just this width to spacing ratio, which is a square root of a times p. P being just n over, a being n over m, and p being j over m. And we found that, I mean, we found just an explicit form of the kernel, and it depends on this width to spacing ratio. Of course, as I told you, width to spacing ratio changes from place to place in the spectrum, but locally you have it, and you know it, and it is a times p is, roughly speaking, the square of the width to spacing ratio. It depends only on that. And then, well, it was also well, in slightly different form, just found also by Liu, Wang, and Wang. And you see, I mean, the function is sort of complicated, and if you have a kernel, it depends on the difference here, first of all. The second of all, well, you have this R5 function, which is imaginary error function, which is roughly error function of an imaginary argument with some minus I in front, coming from the Jacobian. And then you have just real part of that. So what you can do now, you can just ask what happens when you just have a deep system, or if you have a shallow system. So you set a to 0 infinity in this formula, and then what you see that either you recover this, which is just picket fence structure, or Dirac, discrete masses, they are equispaced. Or you get just sign kernel, so which is a standard GUE statistics. In between you have that for any over
Is this, I don't know, maybe it's not correct, but just is this equispaced is related with this triangular law for Lyapunov exponents? That is,
yeah, well, equispaced means actually rectangular, but triangular law found by Newman was not for that, but for squares of that, which of course gives you a triangular.
Okay. So it's related. In fact,
it is exactly the same thing.
Okay.
Yeah, but of course, naturally, when you think we are talking about unfolded spectrum, unfolded spectrum has equispaced eigenvalues.
No, fine.
So, and if the width to spacing ratio is 0, it is delta peaks, and you have no other solution. Yeah. And of course, once you have the kernel, you can just find higher moments or any moments or correlation function, but you also can find just local level density by taking the trace. So you put psi equal to zeta, and you get that formula. Basically what happens is if you put psi equal to zeta, this term drops down, and you get again something which looks like picket fences, and you get from the sign kernel you get a flat distribution. And this is what you see in the if you just plot directly the formula here, depending on the value of width to spacing ratio, which is just a times p squared. And then first of all you see indeed that for width to spacing ratio going to 0, you get delta peaks. It is those gray peaks here. Then if you change it, then you get peaks, and the width of them grows. And then it becomes like that. Finally, when you send this width to spacing to infinity, actually when you send a times p to infinity, then you just get a flat. You get this, the dashed curve, which is a flat solution. It is exactly this one. Well, I will not display for you just a soft edge because it's very complicated. It's again a sum of an certain integral, but you have an explicit formula, and of course, no wonder it again interpolates between the Dirac delta statistics and Airy statistics, which is known for soft edge here. And the hard edge, as I told you, well, you get explicit position of Lyapunov spectra, eigenvalues. So you know where is every eigenvalue located here. And from this you can just derive exactly this triangular law. Because I mean, if you look what is the separation of consecutive peaks is 1 over j. And then from that you can do that. Well, as I mentioned, there is also a very interesting part here in that case when you have a shallow, because if you have a shallow system, you can have J of order n, which gives you exactly this continuous spectrum. But if you take J of order n, which is sublinear function of n, it is close to that one, you get something which exactly reproduces this earthy kernel here. And then if you take J of order 1, then you get again half H. Well, now let's come back to our additive. I was talking today only about this multiplicative stochastic process, but when Gernot gave this talk in Israel last year, in October, Maurice just commented on that. Well, there was a similar situation discussed for this, additive random walk, for Dysonian walk. And they also had a kernel which interpolated between picket fences and GUE statistics. And it was considered in Kurt Johansson's paper just many, many years, 15 years ago. And they got something like this kernel. And the question was, is it exactly the same kernel or not? Just to be more precise, in this paper, Kurt Johansson gave any solution for the kernel for the situation when you have a certain initial conditions and you start to make this Dyson random walk. And the simplest solution he found when you place your original initial eigenvalues as delta peaks on some discrete values equispaced on the real axis. So initial condition is that you start from equispaced guys. So it is exactly our picket fences. And then, of course, those guys start to evolve, and since after some time, each of them does not have delta peak anymore, but has a distribution. That distribution gets broader and broader. Finally, because it is a crowd of vicious workers, they start to repel. They don't want to. They form a continuous here GUE statistics. So the only thing is that in our case, we just interpolated from GUE to picket fences when time grew up. And while here it's just opposite. Initially you had just picket fences, and then after, but the end situation where you interpolated between GUE and picket fences. And the question was whether this was exactly the same as our kernel. So the formulas are completely different. The only thing is that they both include the sum. And then, well, Jacques Vermachot, who was also in the audience, he commented, if they do, that they must do via Poisson summation formula. So that the one is just sort of Fourier, sum of a Fourier modes of the others. And he even just checked that numerically, that for some values, he just looked at that they agree. So then we knew the clue, so we found that Poisson formula brings one form into another. So it is just Poisson summation formula which brings Johansson to ours or vice versa. So it is exactly the same. So the mechanics of the problem is different, completely different. The endpoints, end states are the same, and we believe that the interpolation between them is a sort of universal. And we also checked numerically that you, instead of, well, for example, in our case we just consider independent GNIB. You can make a GNIB which is made of some sort of correlated GNIBs. So you include sum of two consecutive GNIB, G1 and G2, then G2 and G3, so that they are correlated. So you have correlated coupled GNIBs, and what you see here is just local density for a given width to spacing ratio, and they are on top of each other of our prediction. So whether it is, well, independent or correlated doesn't matter. It seems that it is really universal. So just because of that, we like to formulate, well, the conjecture. The conjecture is that local statistics depends on the symmetry class and the width to spacing ratio. Unfortunately, we have only a result for GUE. We don't have for GOE. We don't have for symplectic case. So it's hard to say. But at least we have just a couple of, well, we have a strong evidence that it seems to, at least in this GUE, do not depend on details. So, and we, in fact, we also just consider the sort of Bernoulli matrices, which is made of discrete elements, and they give exactly the same result. So just let me summarize shortly. Well, we discussed here just a sort of propagation, linear propagation through m layers of a system which has n degrees of freedom, and the degrees of freedom are described by complex variables. And we just discovered that depending on the geometry of the system, whether it is deep, shallow, or just sort of critical, you have different local properties, stochastic properties of eigenspectra. And in that case, we just found explicit form of the kernel, and the kernel seems to depend only on this width to spacing ratio. In our case, width to spacing ratio was extremely simple. It was the square root of j over n, so you could measure it and you could. So, well, we know exactly what happens in the bulk, soft edge, hard edge. We just discovered this transitional region between bulk and the hard edge. And at the end, I told you that for some reasons, if you interpolate in Dysonian random walk between picket fences and GUE statistics, you get exactly the same kernel as the one which you get for the product of random matrices. And this drove us to just formulate this conjecture, and it would be nice to check it in the future. So, thank you very much for your attention.
So you mentioned that for other classes you don't have any results for product, say for beta equal for product of semi.
No, we don't. For the moment, I mean, we cannot just multiply Gini matrices.
Real Gini.
Real, yes.
Even finite number.
Yeah, for finite we know quite a lot. I mean, already Newman knew a lot. When you keep n size.
No, I mean keep m finite and n.
No, for m finite no.
But eigenvalues will cross. I think for the it's not determinant of.
But I think that
it's not.
There are some results by Jesper Ibsen and the Forrester on the product of UG. But to take this kind of limits, we have not tried it.
But it would be nice to see the genuine kernel for example, GOE case and what would be just interpolation. We expect that it will be much more complicated, but it's still a challenge, I guess.
But have you also looked at the numerics for GOE? Whether you see a difference between these two cases?
No. So since at least I mean, for example, if you look at the numerics, it's good to have at least something like a reference point. And this looks like a sinus, but it is not. It is just really something which we get exactly from our kernel. And we don't have that curve for GOE, but maybe it would be worth checking whether it is whether it differs or not.
The point is that if it works for IIT Bernoulli, which is real, right? Then maybe it can work for other real matrices.
Okay.
But these are complex Bernoulli. Okay. So
Complex Bernoulli?
yeah.
Okay.
There might be some kind of semantic confusion, because when you look at the real architecture of deep learning, so the number of neurons, which is n, is very large, can go into millions. And the number of layers is not so large, because it can go into, let's say, hundreds maybe, okay? So in some sense, from this perspective,
We are always shallow.
They're always shallow. So deep networks
So
are
it
always
is.
shallow.
I should call them very deep. Sorry. Very deep. Yep.
When summing up matrices like this Dysonian random walk, can one set some parallels to the central limit theorems that we know for single variables?
Yeah, but it is free probability. In that case, it is you have exactly the same theorems in free probability. You can, for example, and Maciej and his group just did that for many cases. For example, initial condition, which is a fixed matrix, then you get this Gini, which is just somehow hermitized, and you add it as a pre-random variables, and it is pre-random variables is exactly central limit theorem for matrices, which are rotationally invariant. So in that respect, it exactly the idea is that freeness you have to add, and otherwise you have exactly the same picture.
Freeness is that they are uncorrelated.
Rotate that eigenvectors are uncorrelated. So, but for Gaussian case, if you have Gini plus Gini, well, conjugated, eigenvectors are completely uncorrelated. They are on the unitary sphere. They are hard measured. So if you have that, then there's a one-to-one map, Berkovich bijection between the two central limit theorems. So you can do everything the same, but the intuition is correct, yeah.
And how about some generalized central? Will the attractors like the Levy limit?
Oh yeah, Levy is unfortunately not anymore, you can build Levy matrices in two ways, element by element. But if you do this element by element, so each element is Levy like random variable, then the matrix is not anymore free, because it favors some directions in the eigenvector space. But you can do this in a different way. You have that, and you rotate it by har and har from that side. And in that case, you can do something. Like you have Levy, and then this Berkovich tells you exactly what to do. But it is an artificial class of matrices, because for Gaussian, if you make it out of Gaussian elements, it is already free. In a sense, it is rotational invariant. But if you do that for Levy, so element by element, it is Levy, it is not anymore rotationally invariant.
Gaussian is the only one.
Gaussian is the only one. So for Levy, you have to artificially just multiply it by U and U dagger, where U is just harm distributed matrix. Then you can do that again.
Okay, do you have time for a question more? No question? Let's